So hi everyone, I welcome you all to the second lecture on thermal properties of matter. So that in this lecture, we have started with finding the effect of thermal expansion on the pendulum base clock. So we begin with, so initially this pendulum is at a temperature theta, that is theta I. Time period of this pendulum is 2 pi under root L by G. We have, as there is a thermal expansion, so there is a change in the length of the rod of the pendulum due to the thermal expansion, because now the temperature is increased to theta f such that theta f is greater than theta I. So Lf is the new length due to the thermal expansion. So what we found out is that the initial time period is 2 pi under root L by G, but now the temperature is increased. So the final time period becomes 2 pi under root L plus delta L by G. That delta L is due to the thermal expansion. So Tf by T will become L plus delta L by L. And so delta L will become, so delta L comes out from that is the change in length that comes out due to the thermal expansion. So that comes out to be L alpha delta theta. Delta theta is the change in the temperature. That is the final temperature minus the initial temperature. So we find out the ratio of temperature time period, final time period to the initial time period. So this is the initial time period. So we get it this to be Tf by Ti, that is 1 plus alpha delta theta to the power 1 by 2. We know that alpha, the value of alpha is very small, such that alpha delta theta should be less than 1. And so we apply the binomial expansion in a way that 1 plus x to the power n become 1 plus nx. So Tf by T will comes out to be 1 plus alpha delta theta divided by 2. And so we get delta T by T. So T is the initial. So the change in the time period comes out to be 1 by 2 alpha delta theta. If someone will going to ask the percentage change in the time period, that is delta T by T into 100. So this you can get. Now I have a question for you, that is, for a seconds pendulum calibrate at 20 degrees centigrade is operated at 30 degrees centigrade. Find the gain or loss in 1 day. So the total, we need to find out the total loss of the calculations with the time period in 1 day, such that alpha is given to be alpha for rod is for that wire is given to be 1.2 into 10 to the power minus 5 degree centigrade inverse, and 1 day has 86400 seconds. Okay, so we need to find out this. Options are 5.184 second, 5 second, 10.368 second, and none of the above. So try this question. Okay, so let's solve this question. So we need to find the gain or loss in 1 day. So we know delta T by T comes out to be 1 by 2 alpha delta theta. So that is 1 by 2. Alpha is 1.2 into 10 to the power minus 5 into change in temperature, that is 10 degree. So it comes out to be 6 into 10 to the power minus 5. Now we know for 1 second the loss is delta T by T. So for 86400 second, the loss is delta T by T into 86400. So delta T by T comes out to be 6 into 10 to the power minus 5 into 86400. So the final answer that we get is 5.124 seconds. So the correct option is, sorry, 5.184 seconds. The correct option is this. Okay. So that's all largely on the linear expansion, coefficient of linear expansion. Now let's look at other kind of expansions, that is volume expansion. So first look at the area expansion. So area expansion is when you see, or we can say when there is a increase in area of material on increasing the temperature of a material. So let's say we have this kind of thin sheet. So we have a sheet that is having a cross section area A, that is initial. Now heat is provided to it and it gets expanded. So the area is increased. That is A prime. So the area gets increased. So that is the final temperature. And similar to the linear expansion, delta A is directly proportional to the change in temperature. Also, delta A is directly proportional to the initial area of the cross section or the sheet. So delta A comes out to be removing the proportionality constant, that is beta A delta T. Now let's look at the volume expansion. So volume expansion is expansion in, that is important comparative to other two. Expansion in volume of a material on giving on increasing its temperature. Okay. So let's say you have a volume, consider a cube for now. Let's say you have a volume. So that is the volume, initial volume, that is temperature Ti. Now you give some heat to it. Heat is given such that volume gets expanded. Volume get expanded. That is final V. And the temperature Tf such that Tf is greater than Ti. So again, similar to other two expansions, delta V is directly proportional to the delta T, and delta V is directly proportional to the initial volume. So delta V comes out to be gamma V delta T. So till now we have introduced three terms. So beta is the coefficient of areal expansion, and gamma is the coefficient of, or we can say superficial expansion. Gamma is the coefficient of volume expansion. So we need, now the question is find out the ratio of alpha, beta, gamma for a rod of length L, area of sheet L square, and a container and a cubical container of volume L cube. So now we have three kinds of system, that is there is a linear expansion. Options are 2:1:3, 1:2:3, C is 1:1:2. We have a system where we have a rod where there is a linear expansion. we have a sheet where there is a aerial expansion or a superficial expansion, and then we have a cube where there is a volume expansion. So we need to correlate this, and we have these three options. We need to find out one. I will give one more option, that is D. That is 2 is to 3 is to 1. Okay. Okay, so let's look at the solution of this. So the solution of this is we have a rod, we have a sheet that is square sheet, and we have a cube. So that is L, that is L square, that is L cube. So these are the initial size conditions, shape and size conditions. Now the temperature is increased. You need to consider it by yourself. There is a heat is given, then only you will get alpha, beta, gamma into them, such that this will become delta L, this will become delta A, and this will become delta V. We need to relate all these with L. So delta L is delta L as it is, or we can call it as DL. Delta V, we can call it del V. So we know V is L square. So we can differentiate with respect to L to get the change with respect to L. That is L cube. So del V dV by dL is 3L square. Similarly, A delta A is nothing but dA, and dA, A can be L square. So dA by dL is nothing but 2L. So we know that delta V or dV is nothing but gamma delta T. All are corresponding. So I can write this in question. So all of them are heated such that the change in temperature for all is delta T. Okay. Gamma delta T into V. So dV we know in terms of length. So that is PL square DL gamma delta T L cube. And we know DL. So 3 is equals to delta T L by DL into gamma. So that is alpha, 1 by alpha. So gamma by alpha comes out to be 3, and gamma is 3 alpha. Similarly, we can do it for area. So delta is dA, that is alpha beta, beta delta T into A. So dA is 3 2L square. DL is equals to beta L square. So that is 2L, sorry. This is 2L, beta L square delta T. So 2 is equals to beta L delta T by DL, and this is nothing but 1 by alpha. So beta by alpha becomes 2, such that beta is 2 alpha. So alpha, beta, gamma we need to find. So beta is, so that is alpha is 2 alpha, is 2 3 alpha. So it will become 1 is 2, 2 is 2 3. That is very important, very frequently asked in NEET and GMEs. Maybe in your board also to derive this. Okay. So that is 1 is to 2 is to 3. Okay. So now we have a question on. So I want to comment one thing on gamma, relation between gamma and temperature. So when you see the volume expansion, we are restricted ourselves to temperature less than 100 degrees centigrade because the gamma temperature curve is like this. Gamma and temperature is like this. That is 200. That is 500. So only from this graph you can infer that from graph that at low temperature gamma increases with increase in temperature for non-ideal cases. Okay, so that is the one thing that I want to point out, and from here we can also say that gamma is largely dependent dependent on temperature compared to alpha. I want to point out this thing that this is there for isotropic tropic solid, like amorphous solid isotropic in nature are isotropic in nature, generally crystalline are anisotropic, where when you change the temperature, then the temperature in a different direction will changes differently. So that is anisotropic, anisotropic. So there is one question on gamma for an ideal gas. Find the value of gamma at constant pressure in terms of P, V, and RT. Options are 1 by T, 1 by PV, 1 by P, 1 by V. I'll try to solve this question. So we need to find out this gamma. We know that PV from ideal gas law, that is PV is equals to an RT, and as gamma is related to the volumetric expansion, so that there and that comes because of the change in temperature. So we need to find. So we know that P dV is equals to an R dt. Can we write this? It is given at constant pressure, so pressure is not changing, and R is anyway constant. So gamma will become. We know that dV is equals to V gamma dt. So gamma is dV by from volume expansion. So gamma is dV by dt 1 by V. Okay. So dV by dt is n R by T n. So dV by dt is n R by P n R by PV, and from here PV is equals to nRT. So it comes out to be 1 by T. So gamma is nothing but 1 by T, or an ideal gas. That means to say as the temperature increases, the gamma decreases for an ideal gas. So this thing, that direct increase in gamma is for solids, not for gases. Okay. So there is one thing that is given in NCRT and we need to discuss is that the anomalous behavior of water. So far we have learned as we increase the temperature of any volume of whatever the material is, the temperature, as we increase the temperature, the volume increases. But what will happen for the case of water? Let's see the graph. So it's the volume and this is temperature. So from 4 degree, as you increase the temperature, the volume increases. But what happened before 4 degree? So before 4 degree, if you decrease the temperature from here, from some T, let's say here, that it is called to be 10 degrees centigrade. If you decrease the temperature from 10 degree to 4 degrees centigrade, then there is a decrease in volume as there is a expansion. So at the same time, there is a reduction also. So now, as it further decreases the temperature from 4 degree, so what will happen? There is a sudden expansion. And that's why we call it as the anomalous behavior of. So this behavior is not normal. That's why it's called as this. So this is the reason. And if you find out the density plot from here, the temperature for the water, so it comes out to be like this. And this is some 4 degrees centigrade. So in cold countries, the water lines gets burst. Lines gets burst. So this has happened because there is we see a expansion with decrease in temperature. Also, many a time you see that many time we saw that as you increase the temperature, sorry, when many times you see in the cold countries, we found we saw that in cold countries there is a ice cover over a lake. That is very interesting. So let's say this is a lake. So there is a lake with many fishes inside this. So that's the lake. So as the temperature decreases, what will happen? As the temperature decreases, the so as the temperature decreases from here to the till the 4 degrees centigrade, the density gets decreases. So as the density get decreases, the load the heavier water goes down and lighter water comes up, and so there is a temperature change. And at a time there will be a temperature that will become 4 degree for all. Now what happened after 4 degree? So that is before 4 degree. If you decrease the temperature further, we are taking it in the reverse direction. So when you decrease the temperature further, then the density then the density gets decreases such that so that the density get decreases. So the density of the top fluid gets decreases, and now as we go along, the density get decreases. It will all be on the top, and only the top fluid get freezed as soon as you reach the 0 degree centigrade. So that's the reason why in the cold season in some very cold countries, only it is covered with the top is covered with the ice, not the complete water. That is because of the anomalous behavior of the water. Now, there is another thing that I have to cover is that is bimetallic strip. That is based on these expansions. Bimetallic strip. The bimetallic strip is generally used in fire alarm. So what happens is, let's say we have this. This is one kind of material, and this is another kind of material that is pivoted on it. So that is pivoted such that this will not going to get detached. So for the first material, alpha is, let's say, alpha 1. For this, it is alpha 2. And let's consider that alpha 1 is greater than alpha 2. So what will happen if you increase the temperature of this bimetallic stream? So that is T initial, T and T final. So what will happen? is TF is greater than TI, such that L1 is, we know that is, so it will, the shape will become like this. Shape will become like this. That is first material, that is another material. And there is a pivoted here. And consider this angle to be theta. So L1 is the arc length of L1 and this is L2. So L1 is, this distance is, so L1 comes out to be, so L2 is nothing but, if this is R into theta. And this, in case of bimetallic, that is X, so that is R plus X into theta, such that L1 by L2 is R plus X by R, and X by R is, and L1 by L2 is alpha 2 by alpha 1, because the temperature change is same. That is R plus X by R. We need to find X by R. So X by R is nothing but alpha 2 by alpha 1 minus 1. Okay. So biometallic strip is generally used in the application of fire alarm. So what will happen if, let's say, this is the alarm and we have attached this biometallic strip to there. So we have attached this biometallic strip here. So as the temperature rises, so this biometallic strip will become like this. That is the biometallic strip. This biometallic strip will become like this, and this will get detached from this. And as soon as it detach, it will give an alarm. So that's the useful application. That's the application of bimetallic strip. So now I want to introduce one more concept, that is thermometry. So better to discuss in the next class. So I will take thermometry in the next class because it's a completely